Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about quantum mechanics, in which this is the extension of the quantum theory, in which it could describe almost any kind of quantum system, as long as it is not really relativistic. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the notes throughout this entire discussion. So let's get started with the idea of transforming a wave into a particle. So what does it mean for a wave to be a particle, and what does a particle has a relation with the wave? So we'll just describe about photons first. So when we have the electromagnetic wave, we will discuss as the peaks to have the photons. So this is where the photons exist. And so if you have lots of these photons, it will later form a distribution, something like this, in which at the peak it is the highest, and then there are the lowest parts as well. So using this idea, you could figure out where is the photon is located at if you know its wave function. And this logic is also true when you're transforming particles into wave. So because of the uncertainty principle, you don't know where the position of your x be, but you could predict where it is. And so this will later relate to your wave function. So this function is something which we will call as psi. So technically, the psi here doesn't truly correspond to the probability straight away. Instead, the psi times the conjugate of the psi corresponds to the probability, or pretty much the probability density. And so there are lots of different explanations as to why it is a complex number, and also why is it the product of both the product of the wave function as well as its conjugate to form its probability density. But I won't fully discuss it here. So this is a property that we'll focus on, and we'll be using it moving forwards. So there are certain properties of psi. So the first property is obviously it is a complex number, and then also it is finite. But not only that, its first derivative as well as the wave function must to be continuous. It has to be. And so this property will later help us define the Schrödinger equation as well as physical systems which truly exist or not. So let's think of a certain type of system in which we have a wave function something like this, in which there's a peak in here. So if you take its conjugate as well, it will later have the same peak. Multiplying them both together, you would have a probability density mostly around this point. And this is where it corresponds to high probability of finding your particle within this place. And so this is certainty in position. But let's say if you have a particle in which it is whizzing around. So remember that you could express momentum as h bar k. So because this is h bar k, we could just interpret this as something like a wave. Maybe it's a complex wave. So maybe it could be at the form of e to the power of I omega t minus kx. Multiply this by a. So maybe this corresponds to your momentum. And so how do you extract the information of momentum from your wave function here? So this is a simple idea. So you could just observe that because this is psi, you could take the derivative of psi here with respect to x in order to get the k outside. So you would obtain negative a ik e to the power of I omega t minus kx. Now, with this, we actually observe that this is the same thing as negative ik of the actual function. So how do you get the momentum? You could multiply both sides by I h bar. So you would have I h bar partial over partial x of psi equaling the h bar k psi, or this is the momentum of psi. And this is what we call as an operator, in which you could extract information from your wave function by using an operator. And so there are lots of different types of operators. One of them in here I will represent is momentum, in which it is I h bar partial over partial x. And there are also some other operators for you to extract information, something like the energy. So we'll try to derive this straight away. The energy is defined to be half mv squared plus the potential energy. Sometimes it is denoted as V. So if you want to extract information about the energy of a certain system, you could have the operator of psi. So you have the operator of the energy applying on psi, and half mv squared, this is p squared over 2m. So we could write this as over 2m, and then the square of ih bar partial over partial x, which is negative h bar squared partial over partial x squared of psi plus v of psi. And this is what you call as the Schrödinger's equation. So the Schrödinger's equation pretty much tells you the energy of a certain system, as long as you know its wave function. So here's something for you to note. Operators are not exactly the variable that you are interested to taking out of. It's instead something that you're applying to the wave function in order to get certain information. It is not this. It is like if you have a machine which you give it a psi and then you have this p hat, it will later give you the momentum. So the p hat in itself is not the momentum, but if you apply it towards the wave function, it will become your momentum. So something from the previous idea, in which we have defined the probability to be psi times psi star. And so if you know about probability, in the end, if you sum all of these areas from negative infinity to infinity of your probability, psi times psi star, what you would obtain is this must be equal to 1. So this is what we call as the normalization, in which your wave function, if you multiply by its conjugate and then you take the sum over its entire area, the area should be 1. So something also to note about the wave function is that the wave function is, so you could do superposition with the wave function. So it is pretty much something that's linear. So if you have a solution, psi1 as well as psi2 from your Schrödinger equation, which pretty much solves the wave function for a certain system, if you sum them both, as long as they are both the solution of the Schrödinger's equation, the sum of it and as well as the multiples of it will correspond to another wave function, which is also a solution of the Schrödinger equation. So let's do an example. Let's try to solve for a system in which it's something like this, in which when x equals to 0 until x equals to L, the voltage is 0. And other than that, it goes to infinity. So this is what we call as the infinite square well. So let's try to solve this one-dimensional problem first. So just by applying Schrödinger's equation, you could straightaway figure out that E psi must be equal to negative h bar squared over 2m partial squared psi over partial x squared plus 0 is going to be the solution for 0 is less than x, which is less than L. But anything higher than that, E psi equals to negative h bar squared over 2m partial squared psi over partial x squared plus infinity times psi. Now, here is the thing that you need to know. Energy couldn't be infinite. Otherwise your universe doesn't even fit into the scale. So, therefore, your psi needs to be equal to 0. So, psi equals to 0. And this pretty much solves your Schrödinger equation for x is less than 0 and x greater than L. So with this, we could actually straightaway solve your Schrödinger's equation. So we know that when psi 0 should be 0 and then psi L should be 0. So let's just solve this Schrödinger equation, equation 1. So if we try to solve this, you would gain E psi will be equal to negative h bar squared over 2m partial squared psi over partial x squared. Now if you have already known about differential equations, you would know that the solution will be psi equals to e to the power of the square root of 2me over h bar, multiply this by I, x, well, plus or minus. And this is pretty much your solutions. So it's ae to the power I square root of 2me over h bar, x plus b e to the power negative I square root of 2me over h bar, x. And so if you have already learned also about complex numbers, as we have discussed from the idea of the LCR circuits, we could decompose this into cosines and sines, and you could figure out what the a and the b is related to each other. But we could also do it from this case, because we know that psi 0 must be 0. This means that your solution has to be a plus b must be 0. And so this is when x equals to 0, but when x equals to L, well, actually we could just plug it in first. This means we know that a e to the power of I square root of 2me over h bar, x. Subtract this by e to the power negative I square root of 2me over h bar, x is one of the solutions. So we could express this again. This will be a, multiply this by, we could multiply this, no, sorry, because we know the property that e to the power of ix minus e to the power negative ix over 2i is sine x. So this will be, so I will later discuss about where to get this on the foundation of mathematics. But this is a property that you need to remember when you're talking about complex number exponentials. So this will later become, so it's 2i will be combined into your a. So a is a pretty much already a complex number. So you would have the a, multiply this by sine the square root of 2me over h bar x. So from here we have two different variables that we could actually choose. So let's try to figure out when x equals to L. Maybe that will give us much more information. So when x equals to L, this will correspond to a sine the square root of 2me over h bar, multiply this by L. And this must be equal to 0. And this gives you information that the square root of 2me over h bar times L must to be n times pi. So we could solve for this. So this would mean L would, no, sorry. We could figure out the E to be h bar and pi squared each. Each of them are squared, this n, sorry. Divide that by 2m. So you can simplify this further. This will be h squared n squared over 8m. And this is quantization of energy. Since we put in the n, in which n is a natural number from here, n should be an element of the natural number. And what we figured out is that the energy must be quantized, proportional to n squared, pretty much. So this gives you certain states for your wave function to be able to propagate at. And this is related to the quantization of energy that we have discussed previously. So this is exactly the model that we need to describe the Bohr's atom or photoelectric effect and etc. So sometimes this n here is something which you call as the quantum number, in which it pretty much tells you the state of a particular wave function. So this is used when you're talking about the atom. You would normally have 4 different numbers for you to discuss the orbit of the electron. And it is all related to the quantum numbers. Another thing to talk about is that you could figure out the ground energy, and it is when the n equals to 1. So ground is when h squared over 8m is your energy. So we could actually just substitute everything back into your equation. So what psi is, it's going to be a, multiply this by sine of, the sine of n pi x, I think. Yeah. So this is the solution. Oh, sorry, this is n pi x over L. Yeah. Sorry, I missed some numbers here. So this would be 8mL squared. There we go. So this should be true now. Yes. So you could see here that you could change the n to correspond to different energies. But what about the A? Well, the A could, well, you could actually solve for the A because you know that there's a property of the wave function in which it must be normalized. So if we multiply this by the conjugate, what you would obtain is this is A times the A star. So it's the magnitude of A squared. So sorry, this is the integral from negative infinity to infinity, or 0 to L, because from negative infinity to 0, it's 0, and from L to infinity, it's also 0. So you would obtain this, multiply this by sine squared n pi x over L dx. And so this could be written as 1 minus cosine x, cosine n pi x over L times 2 over 2. And so doing the integral, what you would obtain is that 1 should equal to the amplitude of A squared. And then there's the 2, meaning that this will be multiply this by L over 2. And then the cosine of 2n pi x over L would later turn out to be cancel out to be 0. So your A, so one of the solutions of A is square root 2 over L. So if you plug it in into your wave function, it will later form the functions that you need. So if you want to try to visualize this, this is the quantum well. And so the lowest energy will have something like this. So the length is pretty large, and then going higher, it will correspond to a much more, there's much more nodes that is hitting the 0. So something like this could also work. So from here, you could actually figure out the probability. So the probability will later also correspond to something like that, but let's draw this. There's something like this, and then it's this, and then it's like this. So each of these values corresponds to probability of 0. And so this is weird. If you're thinking about a quantum system, and then you put a ball inside your box, and then you jiggle it around, what you would expect is that you could find the ball at almost every different point as something which is similar to the ground state. But it is also not true that the ground state is true, because you could find the ball to be at the edge. But when you're going to higher state, there are much more places in which the probability is 0. So it doesn't make full sense that this is correct. But if you extend this towards infinity, when n goes to infinity, in which the energy is pretty large, you could actually observe that your system would have probability which is something like this. And so this bar here corresponds to a uniform probability. Well, almost uniform, because there are still some zeros, but it's almost negligible, to the point that you see your system to have all of the possibilities that your particle is located at a certain place. So another type of example that I won't fully discuss about is the harmonic oscillator, or the quantum harmonic oscillator. Harmonic oscillator. So this is normally denoted for the potential to be half kx squared. And you could solve this differential equation by using polynomials, by using other methods like even operator algebra. But in here, I will just present the solutions. Well, the solutions itself for the wave function is something that is pretty advanced to study. So I will skip through and talk about the energy. The energy is half plus n, multiply this by h bar omega, in which omega actually corresponds to the square root of k over m. Now, if you think about this, if you increase your n, this will later be something very similar to the probability will be very similar to the classical model. But if you think of it in terms of quantum, there would be nodes. And there are ways for you to solve the Schrödinger's equation graphically. So I will just show this straight away. And so the logic comes from so it's E psi equals to negative h bar squared over 2m partial squared psi over partial x squared plus v psi. Now you could get the idea that partial squared psi over partial x squared corresponds to 2m, multiply this by v minus e, divide that by h bar squared, multiply this by psi. And this gives you certain information. So let's actually do a little bit of sketching. If you have a function, so let's actually separate this into two. If the v is larger than e and when the v is less than e. So when the v is larger than e, if you have a function which is already above the x-axis, it's going to have a curvature which is positive. So a positive curvature means that it will be going upwards. So it will have this shape. And for negative functions, it will have something like this. But for the potential energy less than the energy, this will correspond to something like this. So this is if the energy is less. So this is not enough energy, not enough E, and this is enough E. So we could try to sketch the solutions of the harmonic oscillator. So we could just sketch your V first, which corresponds to something like this. And then let's actually try to draw some functions. So we could start from this guy here. And so we will just state that the energy is pretty small for n equals to 1, let's say. So you could sketch this as something like this. So this is your energy, let's say. So the function could go something like this. So for positive, if your energy is much more higher than the voltage, it will be something going downwards. But then when it hits this intersection, it's gonna correspond to the function that is trying to go away from the x-axis. So what if the solution is something like this? But if you have higher energy, let's say somewhere along here, instead of only having this one solution like this, instead what it could correspond to is something like this. So it could be going like that. So higher energy corresponds to more nodes within the wave function. And you could increase this much more further, and then if you try to find a probability, there will be some nodes within your quantum system. And this is expected. So another thing to point out about the solution of the quantum harmonic oscillator actually corresponds to a very interesting feature of photons, equals to nh bar omega. This change of this h bar omega is a very clear indication that almost every single system that we observe could actually be transformed into some form of a parabolic potential as long as you're taking very small changes in x. So almost every single models within the entire within our universe actually has a correspondence to this n h bar omega. So this is where almost every single system that you have is quantized by a factor of h bar omega. So another thing to talk about is quantum tunneling. So quantum tunneling is pretty much the idea where if you have a potential, and then if you give it, and then if you apply a certain energy, let's say this amount of energy, so this is your energy, this is your voltage, what you would observe is that there will be a probability that you could find the particle on the other side. So let's think about this in a graphical way. If we try to sketch a wave function propagating like this, and then when it hits this location, oh sorry, let's just draw this in a better way. So if we have the wave function like this, it's propagating with certain velocity, and let's say that its energy is not enough to penetrate this barrier. What ends up is that because of the Schrödinger's equation, you could actually sketch that there will be a declining potential that's going down in here. You could see. And so you could still observe that there is a particle within the barrier, which doesn't make sense classically. But then you could still observe the particle after the barrier, which makes almost no sense at all. So this is what we call as quantum tunneling. And you might be thinking that this is not really conserving energy. But it turns out that it is. Because if you actually measure, if you figure out the position, you don't know its momentum. But if you know its momentum, you don't know its position. So it makes sense in terms of the Heisenberg uncertainty principle. But also you could observe this from the energy as well as the time. So if you know the energy very well, you don't know where the particle is located at. But let's say if you know when the particle is inside the barrier, let's say you find it in here, its energy could be much more higher or lower because of the uncertainty principle. So this is where I will state from now on that you need to throw away everything that you know classically and start thinking in a much more quantum mechanical way, because every single object that you have is behaving much more like a wave, but it's very negligible. So instead of a barrier, we could also try to think of a well, something like this. So if we have a well, and then we have a certain amount of energy, let's say in here, you would observe that your system would have bound states. So the probability will be mostly contained within the boundary. It could be something like this, it could have something like this, and etc. But here's something to note. Based on the idea of the quantum tunneling, there is also some leakage outside of the well. And this comes from one of the properties of a wave function, is that it has to be continuous for its first differential. But observing this with a infinite potential is something that's physically impossible. So this is why the idea of the infinite square well is a very good thought experiment, but it doesn't really exist throughout the entire world. It's almost like an approximation. So anyways, we have these bound states in which it corresponds to quantization of energy. But if you have energy which is higher, your particle will end up behaving like a free electron. So it could whiz around, and then there is much more velocity, and then there's something slowing down. So it's like water going through. If you have water going through, when it is at the well, it is traveling much more faster. And it actually makes sense. So the idea of bound states as well as unbound states are both related on the potential. So if you have your potential to be bounding your energy, what you would have is that these bound states will have quantization of energy. But if, let's say, it is not bounded, if you have energy in here, what you would have here is a continuous energy. And this also comes from the Schrödinger's equation solutions. And so this means that for anything that has boundaries, it means that the energy should be quantized. But does that mean that for certain systems you should have a continuous energy? And it turns out that this is not the case, because when you're talking about the universe itself, you could always find certain areas in which it is restricted. And so this is where bound states appear, even though it is something that is not really observable. It is something that you couldn't really observe when you're talking about something in a very small scale. So this is why sometimes we could actually neglect the quantization of energy when it is unbound. But technically it is always quantized. So after all of this time, we have been discussing about quantum mechanics within one dimension. But what about within 3 dimensions, let's say? And so the only change that we need to do is that we could write this Schrödinger's equation as something like this. Nabla squared psi plus psi v psi would equal to E psi. Now this nabla here corresponds to the Laplacian. Or the Laplacian is pretty much partial squared over partial x squared, partial squared over partial y squared, and partial squared over partial z squared. And so this pretty much corresponds to the momentum throughout all 3 different directions. And because of this system, you could sometimes have states in which it has the same energy. So you would have different states with same energy. And these states are called as degenerate states. And so degenerate states are very observable when you're talking about the atoms, in which you would have px, py, and pz, in which they have the same energy, but they are completely different states. And this is also true when you're talking about 3-dimensional systems. You could sometimes find degenerate states. And where does these degenerate states come from? It actually comes from the symmetry. So if you have symmetry within your system, you would obviously get degenerate states. So something like the atom, it has radial symmetry. That's why it has degenerate states. And the same thing as if you have a free electron whizzing around within 3 dimensions, you would also have degenerate states, because going in the x direction is the same thing as going in the y direction, which is the same thing as in the z direction. Or it is translational symmetric, or maybe even rotational, or reflection. Finally, to end the discussion of quantum mechanics, I want to discuss about the merging of relativity and quantum mechanics. So combining these two together, if you remember from before, relativity gives you the equation E squared equals to P squared C squared plus MC squared, everything squared. And from quantum mechanics, you got Schrödinger's equation. Now, if you combine them together, and this is what Paul Dirac did. And so when he combined these 2 equations, well, technically not really the Schrödinger's equation, but it is one form of the Schrödinger's equation. What he observed is that from his equation, he found that if you actually take the square root of this, there will be a plus and minus sign. And what physicists did back then was that they neglect the negative sign, because it doesn't make sense for a system to have negative energy. So we have been observing positive energy all along. But when negative energy appears, what Dirac thought was that there should be a particle in which it has negative mass. And this is what you call as antimatter. So the positive sign corresponds to matter, and then the negative sign corresponds to antimatter. So what antimatter has is that it has reverse properties of the matter, except for the mass. The mass is the same, but it's negative. So all of its signs are pretty much changed. So if you have an electron here with certain mass, certain charge, antimatter has a certain mass for the anti-electron, or something called as the positron. It would have the positive charge, which has the same charge as the electron, and then you would have negative mass and negative spin, and much more. So this is the first observation that Dirac did from his equation of relativistic quantum mechanics. But not only that, from the equation that Dirac has, he actually figured out that electrons come with two different tastes. One of them is spin up and the other is spin down. And this is actually observable when you're looking at the spectrum of hydrogen. You could see that there are certain absorption spectrums that is not really observable, that is very negligible. And the same thing is true for the positron. So there is the up spin and the down spin. So each of these corresponds to the same equation within the relativistic quantum mechanics equation for a free electron. So this idea of the antimatter actually shapes a realm of physics known as particle physics. And something that is known to particle physics is that, let's say if you have an electron merging with a positron, let's say they both have certain energy, and then when they combine, they should both emit some energy out in terms of photons. And this is something that physicists has already done multiple different times, in which they collide positrons and electrons and other matters and antimatters to form much more interesting particles. But also there is the idea in which you could actually combine two different photons, h bar omega, to form these electrons and the positrons, as long as you do it in a certain manner. So this is something that I will later be discussing a little bit when we are dealing with the very final chapter, in which we discuss about quarks. But for now, I want to keep this back in your head just to remember that electrons have spin as well as their antimatter counterparts. And so that's all for the idea of quantum mechanics that we'll be discussing for this video. And so thank you very much for watching, and also remember to like and subscribe, and also please share this to your friends who really need to understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.